So suppose, for example, I was told that I have to work with a plane, okay? And I have to make sense of. So secretly, I want to work on the circle, but for various reasons, I've been forced to work with a plane. Okay? So instead of integrating, say, I want to do some integrals on the circle. I take some functions to the circle and integrate them on the circle. But for some reason, I need to work with a plane. So instead of functions on the circle, I have a bunch of functions on the plane, which are scale invariant. Say I want to do some integrals, make sense of some integrals like this. Okay? With a secret understanding that what I actually want to do is to do integrals like this. Say. Okay? So roughly, the idea is that I want to take this integral and remove the part that corresponds to scaling transformations, to the radial direction. Okay? And it's convenient to do it. So a very nice feature of this picture is that, right, these directions I want to get rid of are associated to a symmetry, to scaling. I would like to use that fact to do something useful. Now, first of all, I should probably work with an integral which is scale invariant if I want to do that. Now, this is fine, but here, let me just put something which will make everything scale invariant. So you see, if I'm allowed to use polar coordinates, I'm just going to write this as an integral of, r dr d phi f over r squared. So I guess something like r dr. And morally speaking, I want to get rid of the r dr, which gives me infinity. And it literally is the integral over this rays. Now, sometimes though, so a simple way to do this is to just put a delta function of the radius. Okay, I can say, okay, I put delta of r equal to 1. Or perhaps r squared, so I can write it nicely. Okay, if I do that, I just get immediately what I want. This is going to force the integral to live on this circle. It's going to kill the radial direction, and done. But perhaps I'm not so lucky. Perhaps somebody is forcing me, for example, to do everything in a way that, for some reason, it might be that I don't have, I don't know that there is a nice choice of a circle. Okay. Perhaps somebody is forcing me to gauge fix for some bizarre reason, like that. So it's saying, okay, I don't want you to use this delta function. Use the delta function for some other f of xy, such that f of xy equal to 0 is this yak. Okay? Or perhaps I'm even less lucky. Perhaps this f of xy equal to 0 does like that. So sometimes it catches each ray once, sometimes it catches it 3 times. Okay. So how do I compute the integral I'm interested in if somebody is forcing me to use such a unfortunate choice of delta function of gauge fixing? Well, let's see. What happens if I take this delta function and I check what's the result of integrating over one of these rays? Okay. So I said I have a symmetry. So the symmetry of scaling transformations, I can write it like that. Okay. So notice that this r dr was really just dt. Okay. That's infinity, infinity. So I want to check, okay, if I'm using this Hopf delta function, what do I need to do to make sure that the integral over the rays gives me 1, so I can throw them away? Well, let's do it. Okay. Now, if you remember, when you have integrals like this, the result is a sum over all the points such that f of t star is 0. Okay. And then you of 1 over the absolute value of f prime of t star. This is a general formula about integrating delta functions. Mm-hmm.
So this only works if you have simple series of f, right?
Sorry?
This only works if f has simple series, right?
Sure.
So
that's right.
Case, but for example, if I have this kind of scale invariant gauge fixing.
Right, here it's going to be a mess.
Yeah, exactly.
Sure,
so
that's true.
What should we do in that case?
Oh, wait for a moment. Okay. Also, let me put some f of t here. And here I get f of t star. Okay. Now, this means that if I do this integral, the result is actually quite nice, because I get a sum of over the points such that f of t star is 0 of f prime over absolute value of f prime, which is just the same as the sign of f prime. Okay? So let's see what that means here. Well, here I'm crossing, I only want one place where f of, so let me say f of t is f of e to the t x, e to the t y, okay, in that case. So with here the places where f of t is 0 are, here is just 1 point, okay? So I get 1. Also, suppose that f is smaller than 0 inside and f is bigger than 0 outside. Okay. So this means f is increasing as I cross the boundary. So I really get 1. So the result of this integral is 1. Now I do this. Here I intersect on 3 points. Except that here f is increasing, here is decreasing, here is increasing. So the answer is actually 1 minus 1 plus 1, which is 1. In other words, this integral, the integral of f prime of t delta of f of t, the t, is constant. Actually, let me put something to remember that this was really, okay, yeah. So this integral is constant, independent of x, of the choice of ray. Okay. So it doesn't matter if my gauge fixing condition is good or not so good, or maybe even not transversal. And then when you do this integral, you just get 1. So this seems to be a good way to get the answer I want. I'm going to insert 1 inside this integral. So no matter what my f is, as long as this contour of f equal to 0 surrounds the origin, once I get 1.
It's important this f has nothing to do with the other f.
Sorry? Sorry, yes. Thank you. Thank you. Every function is f. Okay. So this integral So I put 1 inside my integral. That didn't change it at all. Okay. And then you can just do a coordinate transformation. Replace x with some x e to the t, sorry, e to the minus t, and y with some y e to the minus t. This integral, everything inside, everything in this part of the integral was invariant under this scale transformation, so nothing changes. The delta function is still there. Now, for convenience, let me define df over dt, d of f of e to the tx, e to the ty. Let me just call it L of f. So here I can just put L of f xt, xy. And then I'm left with my integral over the t from minus infinity to infinity. So this, which is what I wanted to get rid of. Okay. So this integral is by construction literally the same as the integral I wanted to discuss originally. But it has the advantage that now I'm working on the plane, and I'm using whatever delta function somebody had forced me to use. Mm-hmm.
What happened with the integral over t?
So I wanted to get rid of it. So if I have the integral over t, I get I leave the integral over t. But I didn't want this part. I wanted this. Okay, it's not a very good way to say it.
This is, for example, the analogy of calculating the Faddeev-Popov determinant in gauge theory.
We'll get there.
So in this case, the integral of t will be like the volume of the gauge group that I'm considering.
Yeah. So I mean, here I could say it very concretely. I can parameterize x to be e to the t cosine of phi, y to be e to the t sine phi. Put it inside here. And I'm left with an integral over t of this delta of f prime, which gives me 1. And then this gives me the integral I want. So I'm sorry for this getting rid of integral of the t. It was a bit of a silly way of saying it. Okay, but so this is the point, that this the correct way to gauge fix this integral in such a way that gives me what I want is to put the delta function that I've picked and then add this correction. And then things are very robust. This is really picking one ray. I mean, each ray will contribute to this integral once, with one, no matter how many times my gauge fixing condition winds around or how ugly it is. Which is nice. Now, let's go back here. So why is that this integral was so nice? Why is it that it gives me just an integer, a number which does not jump as I deform my f of t? So the reason is, I mean, almost tautological, is because this is sort of a topological quantity. Now, there are various ways to describe this fact. Geometrically, there is something called, I don't know, if you have seen differential forms, you might have seen something called the Poincare dual of a cycle, of a manifold. So typically, if you have some space, okay, and submanifold, analog to that gauge fixing condition, you can define a form that is dual to this manifold in the sense. So it's a form that is typically either a delta function along the manifold, or maybe it's a bit smeared around. Doesn't matter. So it has the property that if you integrate this form on some other manifold, this just gives you the intersection between M1 and M2. So it simply this integral simply counts the number of intersections with sign, the analog of this sign here, in such a way that the result is topological. So you can move this around, you can move this around, as long as you do topology. If you do it continuously, this number does not change. On the other hand, if you're working in quantum field theory, probably we don't want to think about submanifolds in the space of all fields in our path integral. So there is a bit of a different way to understand this topological invariance, which is to use what's sometimes called topological field theory. Now, sorry, I cannot hear.
You mean the intersection number of M1 and M2?
Yes.
Not the set.
Sorry. How do you denote the intersection number? I forget. Well, let me just say, roughly the number of points. So it's a number counted with signs. Okay, so let's try to rewrite this integral in a way that looks a bit more physical, okay, closer to something that we compute in physics or in quantum field theory. First of all, the delta function is ugly. So I'm just going to rewrite it as a in Fourier transform. I add an auxiliary variable b, and I write the delta function like that. Okay, that's easy. Now, to write this derivative, I'm going to do something that perhaps does not look very natural. So I'm going to add Grassmann-Odd variables. Now, at this point, you need to tell me if you've seen Grassmann-Odd variables in path integrals. I think so. OK, good. So I'm going to add other variables b and c. And something like that. So when I do the integral of B and C, it just pulls down F prime. Now this might look really a bit of an overkill, but if you do the higher dimensional generalization of this, where you have several coordinates T and perhaps several gauge fixing conditions, then the formula becomes something like like this. So there is a determinant now, right, in quantum field, imagining quantum field theories of some functional derivative. So in quantum field theory, this would be the determinant of some functional derivative, not something you want to do directly. So what to do is to do it with ghosts, with these fermionic variables. I'm sorry, the square root of -1 and I will look like the same. I assume, I will tell you in advance, I will never put the indices as number. Okay, when I see an I outside of a subset or superscript, it's just square root of -1. Okay, so this is just a nice way to rewrite this integral. But it also makes can be used to make the topological nature of the problem manifest. So we thought understand. See, in that geometric context over here, right, we're talking about forms, differential forms. I said that you could represent this delta M1 in many ways, this delta function here, perhaps something's mirrored. Right? Those were statements about forms. And there are statements like, delta M1 is closed. And that's why it doesn't matter how you deform M2, you get the same answer. And perhaps delta M1 is defined up to exact forms. And shifting by exact forms, this does not change. Okay, so you've not seen that differential forms, this words will mean nothing. If you've seen differential forms, you see that there is a lot of mileage to be gained just by having an operation which squares to 0 to 1, which squares to 0. And with the properties that if you study things that are killed by this day, they are robust, and the results do not change if you change them by day of something. So let's try to mimic that in quantum field theory. So I'm going to define an operation Q with the property that Q squared is equal to 0. So this operation, so if I want things to be, I want this operation to be useful, I must define it in such a way that things are, all things that you see are Q closed, are killed by Q. And if I want it not to depend on something, the dependence better be Q exact. So what does it mean? So in general, if I'm doing some integral, and I have some fermionic symmetry like that, and I'm integrating a bunch of things. Okay, and Q of Fi is 0, then I can, and also the integral of Q of something is 0. Then the answer to this integral will not change if I shift one of them by Q of something else. Because I can rewrite this as Q of everything. So this Q acts like a derivation, like a transformation, an infinitesimal transformation, minus, say, QF1, F2, F3, G, minus F1, QF2, F3, G, minus F1, F2, F3, QG. Sorry, QF3, G. So these are all 0. This is 0. So putting Q exact things in the integral will give me 0. So whenever I have a structure like this, I have some derivation, some infinitesimal transformation, which can be integrated by parts, in a sense. And I study the integrals, the correlation functions of Q-closed things, then I can study them up to Q exact things. So if I have a set of, the set of interesting things I can study is the set of Q-closed modulo Q exact. And sometimes, there might be a lot of things that I can work with, but the space of Q closed minus Q exact might be very simple. So although I'm studying something that looks complicated, the answers are going to be simple. So that was the case here with differential forms. The differential forms themselves can be very complicated. There are infinitely many differential forms. But if I work with closed modulo exact, I get just numbers of intersections, topological quantities. Here, how do I make sure that this is? Here I'm studying gauge fixing, right? This F was a choice of gauge fixing. So if I want my answer to not depend on my precise choice of gauge fixing, then I better cook up things in such a way that this whole thing is Q exact. Okay, now after all this work, let me just define Q. So define so the QT is C. QC is 0. And QB is capital B. And QB is 0. So see, I've sort of paired up the fields and defined the action of Q so that I act on one of them, I get the other, and then I act on the other one, I get 0. Let's sort of make sure that Q squared is 0. Here I'm sort of assuming that the symmetry I'm playing with is abelian. See, I had just this integral was just an integral or something that looks like, R to the n or a circle to the n.
Why did you choose it this way rather than the other way? You could have chosen.
No, indeed. So this can be generalized in a straightforward way to something that is non-abelian.
No, sorry. I just mean, you could have said QC equals T.
I could have.
Would be fine.
Yes, but this would not have been Q exact. So the nice feature is that this, if I do now Q of BI Fi of T. I probably should have put an I here, sorry. I get precisely BI, or maybe a minus I. Don't pass my signs in general. So you can act on B, you get I minus IB IFI, or you can carry Q across B, pick a minus sign, and act on F. So this gives you minus BI dA of Fi CA, which is exactly this action we had here.
One question. When you write this integral of the delta function in terms of these Grassmann variables, capital B is not a Grassmann variable.
No, it's just a bosonic
okay, so if
variable.
I act with Q on little b, which is a Grassmann, how come I can get a...
Because Q is Grassmann odd. That's right. So I probably didn't test that. So Q is Grassmann-Odd. This is Grassmann-Odd symmetry. So you might ask, how comes it's an analog of this D? Well, when you study differential forms, it's often very convenient to think about dx as actually Grassmann-Odd.
And how do you get the last term? How do you get the derivative when Q is acting on Fi?
Well, I said how Q acts on T. So, and I want Q to act as a derivation. So I want, in general, Q of AB, A1, H2, to be QA1, H2, and then plus or minus, depending on the parity of this guy, A1, QH2. So if you do it on powers of T, you'll see that it acts as a derivative, and then you extend it to any function. Okay. So as I mentioned, I was treating this T as sort of an abelian symmetry transformation, something completely flat, so that the we can quickly amend that. But for now, just observe that just because the action is written as Q of something, it means automatically that if you change your F, that changes the thing up there by something Q exact. And so the change has no effect. That's why we get the same answer no matter which F we pick, as long as F changes in a continuous way. And when the F of T is defined like this, it means I get the same answer no matter which ray I pick. Now, if you want to have some sort of a non-abelian version of all the story, my group of symmetries should be, well, a group. So instead of this integral over the TIs, instead of the TIs, I'll have some group element, G. I have some measure on the group. It's called Haar measure, some measure on the group which is invariant under the action of the group itself. And then I need to, to find a decent action. So I mean, how do I say this properly? So suppose that these GA are the coordinates on this group. Okay. Now, first I need to write something like this. Okay. Now, if this G is a coordinate on some manifold, right, then this C is going to essentially be a vector, living in some sort of Grassmann-Odd version of the tangent to that manifold. Now, when I do Q of CA, there is something a bit more interesting I can do than just set it to 0, which is to use this sort of the structure. So this is the same place. So this is in the same place as the Lie algebra of the group lives. So I can sort of use the structure constants of that algebra to write some. I don't know how to. If I use F again, well, which symbol could it be good? Could be good. Okay, let me just use some E. Okay. So suppose that your Lie algebra sorry. So I can actually do something like that. And now I can check. I mean, this is something generic I could have done. Okay, suppose I try to do something like that.
So Q acting on CA is not QGA, should not be 0.
Indeed, suppose I want this to be, sorry. Well, right, so I wanted to write, sorry, I'm going tentatively, okay. So really, the coordinates are not really good things to act on. So that if I have a manifold, the coordinates should be just something auxiliary. So what I really should be talking about is some function on the group. Okay, some function of this group. Just a function, normal function. So here I should write something like, well, morally speaking, I would like to write something like that. But a correct way to put it is that because I want the C to live in the algebra of this group, I'm going to put here so the derivative of this function. So what does this mean? This really is pretty much f of g minus f of e to the c. Sorry, this is just. Problem is, I don't know how much have you seen of Lie groups, or which language have you? Yes. So, sorry, I need to find the right angle for this. Sorry. Okay, let me just say it like that. So, okay, so there's some group, and I want to make sense of some delta function of a function on this group. Okay. So, so up there I wrote a formula for integrating delta functions on a line. So what sort of formula should I write when I integrate over a group? Okay, so like my group, and at some point I want to do derivatives along the group. Okay. So I need a basis of sort of vector fields on this group, a basis of the tangent space. So I have a bunch of vector fields on the group, which correspond to the different directions. And so these vector fields represent the action, can be thought of representing the action of the group over itself. Meaning that if I write my group elements, say, as a sort of as a matrix, as e to the an infinitesimal group element, sort of 1 plus EA dA, well, these are the generators of your group. Then I want the action of this group element over a point, okay, to give me that point shifted by some vector field. Okay. Or the action over some function of the group okay. So if you know what the Lie derivative you know what it means, what this means. If you don't, this is just the infinitesimal derivative along this direction, the direction of this vector field. Okay, so now I can write my determinant, the thing I was after, as the determinant of the lead derivative in direction A of f of I. Okay. So this is what brings, instead of just derivatives, I get these lead derivatives. The difference between derivative and lead derivative is that derivatives commute. Lead derivatives, not so much. So if you do the commutation between two of these lead derivatives, you get something like this. Maybe I should not use A, B, and C. Just use U, V, and W. Okay. So these are the structural constants of your Lie algebra. They tell you how true symmetry transformations fail to commute. So, for example, if your group was a rotation, so the group of rotation of the sphere, you might get something like, L1, L2 equal to L3, etc. Okay, so if I try to repeat the same tricks for this, right, my action will look like e to the I, bi, fi, and then there will be something like bi, lead derivative I, ca. Okay. Now, this is nice, but now let's suppose I want to define a Q so that this is exact, or at least first closed. First, let's check if it's closed, and then possibly even exact. And when I act with Q, right here, I get this sort of BDF. So when I act on this with Q, I get something like IBI, CA, the derivative of FI, say. That's fine. But when I act on this, perhaps I get minus IBI, the derivative of FI, CA. So that's good. This cancels out. I'm almost happy, except that now the lead derivative itself, the lead derivative of Fi also transforms, right? So I get something like Bi, and then Cu, lead derivative of Vu, lead derivative of Va, f of I, C of I, C of A. Okay. Now let me just carry the C of A here. Doesn't matter. So if the lead derivatives commute, this is a symmetrical thing. This is anti-symmetric because this is a Grassmann odd. So this gives me 0. So when things were commutative, this term was not a problem. But if these don't commute, this doesn't drop out. It's actually equal to E of UAV LV of Fi. So how do I kill it? Well, the way I kill it is by giving an interesting transformation to C. If I have C transform into this, it is to cancel out this term. So that's why when I define the BRST transformations in this symmetry in this context, I need to have things like Q, F of G is the lead derivative, is CA, the derivative of F, but also Q of C is something like E, AUV, CU, CV. Now you can ask, does this square to 0? Now there could be a problem, right? So I can start by computing Q squared of F of G. I get this. and then I act with Q on it. And, well, this is nice. I get C. If I act on C, I get E, A, U, V, C, U, C, V, and then the Lie derivative respect of A. If I act on this, I get C, A, C, V, Lie, A, V of F. We just call this U. Doesn't make a difference. So as long as this is true, these two terms can cancel out. And if you look at U square of C, you need to act with Q on this. You get something like E, A, U, V, E, U, W, S, C, V, C, W, C, S. Now, this is totally antisymmetric in VWS. And this combination, if you antisymmetrize it, is actually the Jacobi identity for your algebra, which is something that expresses the compatibility between double commutators. So as long as your group was actually a Lie group, based on Lie algebra, this is a nice symmetry. And then I can just complete it in the usual way, QB equal to capital B, and Q capital B equal to 0. Okay. So this is not, it's not so trivial anymore. Okay. Got a little bit complicated because of the non-abelian structure of the group. But this integral is still going to be just, essentially 1 or a number, or independent of the formations of F, because it's still true that this is actually Q of Bi Fi. Okay. So this is a way to something like some gadget you can use to get rid of groups symmetries, abelian or non-abelian. Now, so until now, I was just living inside this sort of little theory. Here's a little theory with variables are a group, element in a group, and this B, C, and capital B. And this little topological theory, which is based on a group. Now, what happens if I take this guy and insert it into an integral and try to play the same tricks as I played here? So now I have some integral with some manifold, something. Okay. Or some. So this manifold will have some group action. Which is expressed by some infinitesimal transformations, say. So the symmetry is expressed by some sort of a vector fields over your manifold. And again, suppose that as I was doing here, I don't really want to make do an integral over the manifold. I want to do an integral over the sort of the orbits of this group action. Or I want to gauge fix that integral by picking some slice. Analogous to that picture over there. So, right, so the correct way to do it is to put some delta of f of x together with let me just do it the usual and wavy way. I can, so let me write as xg, the result of acting with g on x. Okay, this is like this e to the t, x e to the t, y e to the t. So let me take my f of g over there to be actually f of xg. Same way as here, I used f of e to the tx, e to the ty. So I can insert 1 in the form, in this form. And this is going to, and as before, I can now just do a redefinition x g to x, like done over there. And I write this integral as okay, apart from the fancy symbols, this is exactly what I did there. And then you get rid of the integral of the group because the group does not enter anywhere here. So this, you could, so this group was, so you can take this as a statement. So this integral by construction is going to be essentially the same as an integral over the orbits of your group of this function we had before. So now we can again rewrite these delta functions, this determinant in terms of these auxiliary variables, capital B and little b and little c. Okay. Now, the point is, so this nice symmetry that I had here, this symmetry. So it was a symmetry of this piece. And here I could have extended it to the whole integral just by saying that qx is 0. So this integral had the same symmetry that this had. Nothing has changed. After I change the variables like that, though, qx is replaced by q of xg. So q of something that depends on g. So it becomes actually CA LA of x. All the other transformations remains the same. So now I get a nice symmetry of this integral. So this is what's called the BRST symmetry. So my gauge fixed integral has a nice symmetry, a nice odd symmetry. And as long as everything I do is Q closed, the result will not change if I change my gauge fixing, my choice of gauge fixing. It's very robust. And this works even if my choice of gauge fixing was pretty crappy. I mean, you clearly see people very worried about gauge fixing. Is the gauge fixing very good? Is it catching the reorbit ones? I'm not quite sure how much of the literature actually makes sense Because when you do things in BRST quantization, I think that this topological symmetry essentially guarantees that everything works. So unless there is some very subtle problem based on infinite, because there is infinite dimensional spaces, I'm sort of, I just don't, I still haven't been able to understand what are they really talking about. So it's word of caution. Don't believe everything you read. So.
Well, in your original integral, what if the orbit, the contour you chose missed the origin or something? You might get
Then you get 0.
So,
okay,
it's not what you wanted.
Well, see, as long as at least on one ray it catches once, that's fine. So as long as your gauge condition was fine somewhere in your space, it's automatically fine everywhere. And usually people are worried about what happens if you go to some funny places, big field configurations. But it's not clear to me that this is obviously a problem. I mean, I think typically the idea is that it's true, things are infinite dimensional. Perhaps you could get in trouble, who knows? But as long as you can find a Q that kind of works and squares to 0, you're typically fine. So indeed, I guess that perhaps these problems can occur if there is some sort of hidden breaking of this BRST symmetry. Your BRST symmetry is broken and cannot be fixed. Then I can imagine that you will really have troubles. But I mean, so these problems can occur, but the fact that they may occur, if they occur, they're going to be very, very subtle. They're not just going to be the result of saying, okay, the gauge choice you made doesn't look, doesn't look like it's cut in the orbits in the one place everywhere. BRST symmetry is very robust. BRST quantization is very robust. Might still break down. But be careful. So anyway, time is almost off. So the point is, right, so this is the, okay, this is the result of the BRST quantization. This is a robust definition of your original attempt of integrating over the orbits, the space of orbits of a gauge group, of having some redundant freedom in the description of your system. So if you have some system, you use too many variables to describe it, and you want to get rid of some. If you can get rid of them by a symmetry, then you can use this formalism to do it properly. And although it depends on this arbitrary choice of gauge fixing condition, it's automatically, as long as the gauge fixing condition changes smoothly, the result will not change. Now, one final remark is that often people would then want to get rid of this capital B. The BRST symmetry is often presented just in terms of X, B, and C without the capital B, which is fine. So when that is the case, you see, if you suppose you want to integrate away B, okay, if you have not, and you have a bunch of operators inside, and maybe some of those operators contain B. Okay. So you can replace B. Morally speaking, B can be replaced with the derivative with respect of F. So suppose, for example, I was using my gauge symmetry to gauge fix away some variable, really getting rid of some degree of freedom, like the metric in the string path integral. Okay, so that this F was really one of the elementary variables of my system. Then having a derivative with respect of F acting on everything else, it's pretty much like putting the equations of motion for F. So when you do quantization of gauge fixing by hand, you use your gauge fixing condition to get rid of some variables, but then you need to remember that those variables were there, the equations of motions for those variables were there. In the context of BRST quantization, the way this happens is that, roughly speaking, after you integrate away capital B, Q of B is the equations of motions for this degree of freedoms F that you are getting rid of. So this means that the equations of motions are Q exact, which is essentially the same as saying they are 0 in the context of this Q cohomology story. So the way BRST quantization makes sure that the equations of motions of F hold is by making them Q exact. So for example, I know in electromagnetic, okay, we'll see examples of these, more concrete examples. Yes, we're more or less done. There was another couple of things I want to say, but I think I can say them next time. I mean, there are simple ways to modify this. If your gauge fixing condition is even a bit worse than this. So, for example, I'm gonna say this right. Sorry, just a moment. Right. For example, it might be that instead of having a gauge fixing condition, which is just a function of your variables, might be that this sort of condition is inconvenient to use. You might want to add some extra auxiliary variables. And have some sort of an integral over these auxiliary variables. And it's relatively easy to accommodate this. I will not go through the details, but pretty much it turns out that I will go through the details in one of the next lectures because we need this for string theory. But roughly, it turns out that this gives an insertion of so if you have a situation like that, you end up having a formula that looks like this, but you end up with an extra integral over these auxiliary variables and some compensating factors. Okay. So this will be useful. But anyway, I'll derive this later. Okay, any questions? I mean, this will be useful in string theory because remember I told you locally, so you want to get rid of the metric. And locally, you can make your metric to be flat, but you cannot do it everywhere at the same time. So you're left with a little bit of freedom on how you glue these flat patches together over to form your surface. So in a sense, you're left. So you're left with a bit of freedom on how to gauge these patches together. Something that's called a complex structure. So you cannot write a gauge fixing condition that says metric equal to flat. You can write a gauge fixing condition that says the metric equals to the metric in some complex structure for any choice of complex structure, for some choice of complex structure. So it's like here, instead of setting f of x to 0, you say f of x and s equal to 0 for some s. If you want that gauge fixing condition, so you're trading around some degrees of freedom. You put a condition that is a bit too strong, but you add some extra degrees of freedom. And then the way the BRST quantization produces for you a nice answer as an integral over these extra degrees of freedom by having this sort of insertions in the path integral. Okay. So we will need these insertions to describe the path integral of string theory. Okay.